All right, so why don't we get started? Please excuse my sniffles. Um, Developed a little bit of a cold. So let's pick back up where we left off. And so last time, oh yes, so the reading has changed. It's now chapter 2, sections 2.1 through 2.2. So where we last left off, we talked about this idea of error, and we filled in more details we filled in more details of the architecture or anatomy of a learner. And we looked at this error measure and different alternatives that should be under consideration for this error measure. And we looked at the fingerprint example and we talked about the different types of errors you can make. And based on the application under consideration, that you want to think about the way these errors are made. And so we'll continue on from this and look at some other considerations as it pertains to training, testing, and the expressivity, how expressive your hypothesis set is. And so earlier in the semester, we talked about Hoeffding's inequality, and we said that Hoeffding's inequality was effectively, you could consider it testing. You're evaluating the coincidence between your in-sample performance and your out-of-sample performance. And we said if you set the right context, you can guarantee that in-sample error and out-of-sample error will track very closely with one another. So then we looked at the learning problem, what happens in training, and we added in to this model the idea that you're going to search through hypothesis space, looking for a notion of the final best hypothesis. And in doing so, we put together a bunch of events, this evaluation of Hoeffding's inequality for each of the big M many hypotheses you might be searching for as your learning algorithm iterates through hypothesis space. And we introduced this quantity M in using the union bound, and M was a notional measure of the complexity of your hypothesis. The bigger M is, that corresponds to a more complex hypothesis set. And a more complex hypothesis set means that you have a larger number of alternatives to draw from when you're trying to find some final best hypothesis G that most closely coincides with your ground truth target function. And as we said, if M is really, really big, well, Hoeffding's inequality, or at least this union bound, falls apart, meaning that E in and E out are going to diverge from one another. They're more likely to diverge from one another because if this M gets really, really big, given a sample size, a number of in-sample points, big N, this right-hand side of the inequality is not going to decay this M term sufficiently enough to make this pack learning model work out. And what that means is that with a very high probability, in sample error E in and out of sample error E out are going to diverge from one another. And that's a bad thing that happens. Okay. Any questions about this? So what we're going to do is we're going to look at this idea of the complexity of the hypothesis set, and we'll develop an idea of complexity that's a little bit more generous. And recall the union bound was a worst case scenario where we assumed the probability of this event, E in diverges from E out by more than error tolerance epsilon. We're going to make the assumption that it's not the worst case. We're going to kind of tighten this bound a little bit to see if we can come up with a better way of representing this idea of out of sample performance, this ability for a learner to generalize. Okay, and so when you think of what this expression inside of the union bound is saying, it's looking at the probability that an undesirable event will occur. So let's assume that we have some event name, we'll call it B, and script B is the event that E in and E out diverges by more than epsilon. And so here, if we were to draw on a Venn diagram, in the case where we're searching through hypothesis space for some final best hypothesis that best coincides with a ground truth target function, we have B sub m representing a single bad event for each of the big M many events that you're searching for, corresponding to your learning algorithm searching through hypothesis space. Now, of course, for a particular bad event that corresponds to a particular hypothesis violating or having a really bad occurrence happen, meaning that E in diverges from E out. So in this diagram, and this is in the book, let's call this mth bad event being that event where E in and E out diverge from one another. We can certainly draw this in the Venn diagram. It's just some circled in area for each of these bad events. And so as you search through hypothesis space, you can imagine these bad events, in the case of the union bound, they're non-overlapping. But that's not the case in practice. And if we can get a more tight bound as it corresponds to the depiction of these bad events, we can actually do better in terms of this multiple hypothesis search when we're considering this notion of generalization, i.e. performance out of sample. And so when we think about this union bound, essentially what we're doing in our worst case analysis, we were saying what is the probability that you're going to get the first type of bad event for the first hypothesis, or the second one, or the third one, or the fourth one, and so forth. And in doing so, with this union bound, we assume they're overlapping, and the rules of probability says that if two events do not overlap, the probability of the union of these events is the probability, the sum of the probabilities of the individual events, right? But something different happens when they're overlapping. It's not a sum, right? Because you don't want to double count the overlapped regions. And we're going to get a lot tighter bound when we make that consideration. Okay? All right, any questions so far? So this is kind of motivating the idea of what happens when you have overlapping events. All right, so can we improve this complexity measure M, where M is the complexity or the size of the hypothesis set? So let's take an example. In this example, we depict with this 2D plane, we're going to depict a two-dimensional feature space. And this feature space, ground truth, some of these points are going to be labeled +1, ground truth, by the ground truth target function. And other of these points are going to be labeled -1. Now, out of sample, we have the shaded region. In this particular graph or depiction or figure, we have the gray region, right? And that's all of your out of sample points, right? Likewise, in this figure, we have the white region, shaded region, and that represents, again, your out of sample points. Now, the gray region are those out of sample points that are labeled ground truth as +1, and the white shaded region are those out of sample points that are labeled -1. Okay, so now we're going to draw a hypothesis. And the hypothesis is going to be a line in the plane. So it's a linear hypothesis in 2 dimensions. And let's consider 2 hypotheses. In this case, we're going to consider this blue hypothesis, the blue line. And then we're also going to consider this green hypothesis, the green line. And I'll take a moment to explain what this graph, what this figure means. Excuse me. And so if we look at the blue hypothesis, when the blue hypothesis classifies points, well, there are points that are ground truth labeled +1, that's the gray shaded region, but there are also points that are ground truth labeled -1, that's the white shaded region. But, of course, out of sample, if we look at the errors that the blue hypothesis, let's call that hypothesis H1, out of sample errors produced by this H1, which is the blue hypothesis line, that's going to be those points out of sample for which ground truth, it says it's one label, and the hypothesis H1 says it's a different label, so it disagrees. So let's take an example look at what that out of sample error might look like for the blue hypothesis H1. So here, this blue hypothesis, it wants to call everything on the upper right, it wants to call it +1 label. That's what H1 wants to do. But we can see here this region, this triangular region, the shaded white triangular region, that's ground truth -1, right? So those are going to be out of sample points because H1 for the blue hypothesis, it says you are a +1, but ground truth, we see that white shaded triangular region, they're ground truth -1, okay? In similar fashion, each hypothesis wants to call that region out of sample for those data points on the lower left-hand side, your left, it wants to call it -1. Now we can see for this blue hypothesis, Well, okay, here's this gray shaded triangular region, and that gray shaded triangular region, ground truth, out of sample, all those points are labeled +1. But here it is. This blue hypothesis says you are -1. It differs in its labeling of the out of sample points. Does that make sense? All right. Any questions? So this is out of sample error for the blue hypothesis. Let's draw our attention now to the green hypothesis. Now, same deal for the green hypothesis. This green hypothesis, it wants to label points that are to the upper and to the right as being +1, right? And so this green hypothesis in its label, it differs in the ground truth for everything drawn from the green up to and including this white triangle here. So is this yellow region plus the white triangle region, right? It disagrees. Those are errors out of sample because that white region plus that yellow region in that upper triangle in the figure are all of those places where the green hypothesis, let's call that H2, where it disagrees from the ground truth class label. Likewise, the green hypothesis, if we look at the lower half, everything down and to the left, your left, the green hypothesis wants to call it a -1 label. Now, of course, this region, both the gray triangle as well as that region up to and including the green hypothesis, it wants to call it -1, but ground truth, they are +1 labels out of sample. And so those are also out of sample errors. Okay, so why did I draw this? Well, we have two hypotheses, H1 and H2, and they're both lines in the plane. And if you look at their orientation, well, the orientation, they're different from one another, but they're not terribly different. It's not like they're orthogonal, right? If you make a small change to the weight vectors corresponding to H1, our blue hypothesis, and H2, our green hypothesis, you can get them to be exactly the same, right? Moreover, right, they're oriented roughly the same orientation. They're a little bit different, but they differ in their out of sample error, right? And so if we look at the difference in their out of sample error, that's where this yellow shaded region is concerned. This yellow shaded region corresponds to the difference in out of sample error between the green hypothesis and the blue hypothesis. Does that make sense? Any questions about this? No? All right. So when we have these bad events overlap, and if we look at out of sample error in this particular figure, we can see that the out of sample error difference between the blue hypothesis and the green hypothesis is not very much, right? Because they overlap quite a bit. They overlap in this gray shaded triangular region, and they overlap in this white shaded triangular region. And moreover, if we compare the relative area for the out of sample regions, it's relatively small where they're different versus where they're the same. So this just begets the point that you have a lot of hypotheses, and you can change hypotheses and still make a lot of the same mistakes, commit the same errors. And so this idea that we alluded to in the previous slide about these bad events that E in and E out are going to diverge, they can overlap quite a bit in the places where they diverge. And so this idea of the union bound, while it is an easy assumption, it is also a worst case analysis because it assumes that all hypotheses are non-overlapping in their out of sample errors. And this clearly demonstrates that that's not the case. Does that make sense? Okay, so here we have the probability of this event that triggers in our Herfling's inequality that E in of the first hypothesis diverges from E out of this first hypothesis. It's going to be roughly equivalent. You know, it's going to be more similar than different from E in of H2 diverging from E out of H2, right? And we just demonstrated that fact. So then the question is, can we use this? And the answer is yes. But can we use this to try to improve on M to make it not such a worst case, to make it more of a typical case? Because as you can see, you can make two hypotheses very similar to one another, and therefore these bad events that Herfling's inequality traffics in are very much so overlapping to a large degree. Okay, so this talks about out of sample error. Now let's look at in sample error. Now, of course, this is what in sample error looks like. Here we have a bunch of circles, And these circles are the in-sample points. And if you take our in-sample points, we have a projection along the horizontal axis, that's one feature, and the projection along the vertical axis, that's another feature. So here you have points defined in 2 dimensions, two-dimensional feature space. And if you were to look at the in-sample error, well, in-sample error corresponds to, for the blue hypothesis, here the blue hypothesis wants to call these 2 points a +1 label, but ground truth, these 2 points, because they're in the white region, they're ground truth a -1 label. And likewise, these 2 points in the gray shaded region, the blue hypothesis wants to call them -1 label for the in-sample points, whereas the ground truth, because it's in a gray region, says, the ground truth target function says, nope, they are actually ground truth +1 label. And so those are in-sample points. And as you can see, between hypothesis 1 and hypothesis 2, well, they don't differ in their in-sample errors for this example. But if we were, and I didn't, I wish I had enough artistic skills to make the circles really small enough to fit. But if I were to put some of these in-sample points in this yellow shaded region and in that yellow shaded region, those would be differences in in-sample error between hypothesis 1 and hypothesis 2. Does that make sense? Okay, so here we have a depiction of what in-sample error looks like. In the previous slide, we have a depiction of what out-of-sample error looks like. And if you notice here, if we take hypothesis 1 and hypothesis 2, from the perspective of in-sample error, their performance on the in-sample points, there's really no difference between H1 and H2, is there? Because they both make errors the same way. And so for all intents and purposes, we could call them exactly the same as far as it pertains to in-sample points, not out-of-sample points. Let's kind of expand that idea. Now, instead of H1 and H2, well, because the weight vectors are real valued, I can have a very large number of different hypotheses that are different from H1 and H2, right? You can imagine this line just kind of tipping ever so slightly, and have a lot of other hypotheses that collectively perform no differently from H1 and H2 as it pertains to the in-sample points, okay? So if that's the case, then maybe we should use this fact that they behave the same way on the in-sample points as a way to try to make this bound M, the complexity or the degree of expressiveness our hypothesis set is, and therefore make this union bound a lot more realistic, and in doing so, get a tighter bound on complexity as it pertains to the hypothesis set. Okay? All right, any questions about this? Does that make sense? Okay, so let's go forward. And this idea of if we can improve M, yes, we can. And we're going to develop this idea of a replacement for M, which at the beginning, when we talked about the union bound, was a measurement of the complexity of a hypothesis set. And we found even for a very simple hypothesis, if you have real valued weights, well, that's an uncountably infinite number of hypotheses. But we don't need every single instance of a hypothesis in order to talk about the behavior, how well they can express how expressive they are. I forgot what I was going to say. We don't need all hypotheses. All we need is a representative that talks about how they commit errors. Because as we see here, H1 and H2 are equivalent, and we have more than H1 and H2 that are equivalent in terms of their labeling, specifically how they disagree with the ground truth target function. So we're going to use that idea of a kind of equivalence class, if you will, to collapse our definition of M, and in doing so, improve upon our worst case scenario, which we derived for the union bound. So in a way, essentially, how we want to count the number of hypotheses, and how we're going to count the number of hypotheses in our hypothesis set is not based on looking at the hypothesis set per se, but considering how these hypotheses can label the in-sample points differently, right? And so we see H1 and H2, they label these in-sample points exactly the same way. So if they label them the same way, well, effectively they behave the same way, and therefore they disagree with the ground truth target function the same way. So if we're going to do that, well, now all we need is just one representative, and that representative is going to be the way that they assign +1, -1 labels to those in-sample points. So here we have our input space representation in the upper left-hand frame. And let's say the pink region is the -1 classification by that particular hypothesis. And the blue region is the +1 labeled output by that hypothesis. And so here, this purple line is our two-dimensional hypothesis, the line on the plane, so it's a linear hypothesis. And so these 3 points here in the pink shaded region, those are labeled -1 by the hypothesis. And then the 3 points in the blue shaded region, those are labeled +1 by the hypothesis. Now, essentially what we're doing, you can imagine removing all of the labels. And if you do that, you can imagine stripping away all the colors associated with the pink shaded region and the blue shaded region. And let's treat all these points the same. So here in the upper right-hand frame, they're all colored in white. Now, given a different hypothesis, well, the hypothesis is going to slice these points into 2 groups. One group we're going to call the +1 group, and the other group we're going to call the -1 group, so in terms of the label output by the hypothesis. So taking those same 6 points starting out, well, one hypothesis, if we chopped it so that the left 3 points are, say, the -1 labels, and the right 3 points are the +1 labels, well, that's one hypothesis that can do it. But you can imagine if that one can do it, a slightly different one can also do that, produce that labeling. A slightly different one can also produce that labeling. So rather than counting all those infinite or uncountably infinite number of hypotheses that produce the same labeling, we only count it once, i.e. that particular labeling. So we're going to use the idea of the assignment of +1 and -1 labels to these in-sample points as the descriptor for a hypothesis instead of the actual weights. Does that make sense? Okay, any questions about this? So in essence, we're taking something that's uncountably infinite, and we're now collapsing it down into these equivalence classes where each equivalence class is a particular labeling or assignment of +1 and -1 to our in-sample points. Well, let's consider a different labeling. Going back to the original data set in the upper right-hand frame, maybe we have a hypothesis that cuts across and lops off or cuts off the top 2 points, right? And so those top 2 points might get a -1 label, and then the bottom 4 points, right, would get a +1 label. That's another type of hypothesis, right? And now certainly, if we can draw a hypothesis that's perfectly horizontal, right, we can also draw one that's a little bit tilted, a little bit tilted, a little bit tilted. And for that uncountably infinite number of hypotheses, we're only going to count once, right? We're going to count it in terms of that labeling where we have -1s, the pink coloring, for the top 2 points, and we have +1 for the bottom 4 points. Does that make sense? Okay, any questions about this? And so this idea of using the labelings, if you think about it, counting hypotheses not by the weight vector values, but by the labelings that they can produce, we're collapsing this uncountably infinite quantity down into a number of discrete alternatives. Beautiful, beautiful part of the theory. So the counts, if you think about it, it's kind of a measure of strength of your hypothesis. If you have a more complex or stronger hypothesis, it's able to express more different ways of assigning these +1, -1 labels to all of these data points. A very simple hypothesis, maybe one that can only go straight across or straight up and down, right? It can only separate them into 2 groups, only a certain number of ways, as defined by the number of labelings that it can produce. If you have something that can be aligned at arbitrary orientations, that's a more powerful hypothesis. Because if you can draw a line, instead of just perfectly horizontal or perfectly vertical, you can draw a line in arbitrary orientations, that's more expressive. It can separate these points into more different types of 2 groups where each group has different labelings, +1 or -1. Does that make sense? Okay, so we're going to use this idea of the way you assign +1 and -1 labelings, different +1 and -1 labelings, as a definition for a notion of a strength of hypothesis set. And in doing so, we're going to collapse this uncountably infinite counts, and when we're talking about set size big M from before, associated with the union bound, we're going to collapse that down into something that we can now manage much more compactly. Okay? All right. Questions? All right. So let's add in some definition. Sorry, let me pause for caffeine. So we have a hypothesis, and the hypothesis takes your data, your in-sample points, and associates each one with either a +1 label or a -1 label. And it can do that with all of the in-sample points from uh, uh, your entire input space. It can do it whether it's in-sample point or if it's a final best hypothesis with an out-of-sample point. Let's introduce this new thing. It's called a dichotomy. And a dichotomy, little h, it inputs a data set. So you see little x1, each of these x's, x1, x2, x3, up through and including x sub n, those are vectors, right? So each one is vector valued. In the case from last frame here in the previous slide, each of these x1, x2, x3, and so forth are two-dimensional, well, really, if you augment it, three-dimensional feature vectors, right? And so a dichotomy is an assignment of a +1 or -1 label. And notice I didn't tell you how these labels are assigned. It's any possible combination of assignment of +1, -1 labels to these n many points, our in-sample points. Okay? So we have a dichotomy, and each hypothesis that we draw from the hypothesis set is associated with a dichotomy. And so therefore, the number of hypotheses, if we take the size of the hypothesis set itself, that can be infinite. But if we look at the number of ways a particular hypothesis drawn from your hypothesis set can produce a labeling +1, -1, that's going to be at most 2 to the n, where n is the sample size, the in-sample size of the in-sample, the sample size, or the size of this set of in-sample points. That's what I'm trying to say. Does that make sense? Questions? So here, you'll notice notationally, here we have number of hypotheses, magnitude of set H. Now I should have said script H, but I don't have the script font when I made the slide. Here we have the dichotomies. So this is the dichotomies produced for a sample size of size big N, right? So you have 2 to the n labelings, an assignment, 2 labels +1 or -1 for the first one, times +1 or -1 for the second one. You do that n many times, it's 2 times 2 times 2, n many times, or 2 to the n power. So this is going to give us this idea of an upper bound on the number of dichotomies that a hypothesis can possibly produce given a sample set in sample points of size big N. Okay? Does that make sense? All right. So because we have this upper bound, essentially what this number of dichotomies means is that if you can generate 2 to the n possible dichotomies or assignments of +1, -1 labels to your big N many sample points or data points, that means that you are fully expressive, right? You can associate any possible labeling of +1 or -1, in this case blue or pink, to your n many data points. That's full expressiveness, right? You're fully expressive. And so this upper bound we're going to use as a candidate, this new upper bound that kind of collapses this uncountably infinite count of magnitude h up to down to 2 to the n. We're going to use that as a replacement for m, right? And so we're going to use this idea of the count of the number of dichotomies that a hypothesis set can generate. We're going to use that as a replacement for that m, which was just the raw size of the hypothesis set. Does that make sense? Any questions? Yes. Yes. So with a dichotomy, you're only focusing on how many different ways does this hypothesis, how many different ways is it capable of assigning a +1 or -1 label to the in-sample points. But before looking at dichotomies, you actually have to take your hypothesis set and you have to try every single hypothesis that's capable of being generated and then test that on the data set. Does that make sense? So in doing so, you're taking, say, this hypothesis straight up and down and the slightly tilted version, you're only counting that as one hypothesis because it's only able to generate one labeling between that set. right? So it's a way of talking about this uncountably infinite quantity, the size of the hypothesis set, and really describing them as equivalence classes based on how they're able to assign dichotomies to input in sample points. Okay? Does that answer your question? Okay. Any other questions? No, make sense? Okay. So we're going to use this idea of dichotomies as a replacement for the sample size. And so we're going to introduce a new concept. And this new concept is called the growth function. And the growth function, little m, it's parameterized by big N, where big N is the size of the set of in-sample points. It's your sample size. So the growth function, it's indexed by h, your hypothesis set. And so you're saying with this nomenclature, with this notation, the growth function of hypothesis set h given n many sample points. And what is that? That's the maximum number of dichotomies that that hypothesis set can generate given n many data points, x. Now, you'll notice here, there's no restriction. There's nothing that says x has to have a particular set of values or x has to be, constrained in the following way. It's a free and open parameter what the feature values are for this x. And what does that mean? It means you can choose feature values for your in-sample points such that they're arranged in any geometry if you want, in feature space. What matters is the number of dichotomies, not the particular values of the feature sample points. And so when you're doing this calculation, it's important to remember that you can have any arrangement of in-sample points you want. They can be together, they can be in a straight line, they can be around a circle. It doesn't matter how they're organized geometrically in feature space. What matters is that you can find some arrangement of data, and given any arrangement of data, the maximum number of dichotomies, assignments of +1, -1 labels to n many data points. That's what the growth function is. Okay? All right. So the growth function satisfies the following property, that we have a growth function, and we know that that growth function has a maximum value of 2 to the n given n many data points. Why? Well, because the most dichotomies that any function, any hypothesis set can generate is just the full alternative of the labelings that you can have on n many data points drawn from a +1, -1 label set. Does that make sense? So we do know for sure that the growth function has a maximum of 2 to the n. So this is a vast improvement. While 2 to the n is still big, it's a lot better than infinity that we had before. And we saw even with a two-dimensional perceptron, you had two weights, W1 and W2. If W1 and W2 are real valued, that's an uncountably infinite number of hypotheses. But now here, we have something that's combinatorial, it's discrete. You know what n the sample size is, so now we know what's an upper bound for a growth function that can produce all possible dichotomies, right? That's the most fully expressive hypothesis set that you can have if it can satisfy all 2 to the n labelings or dichotomies. Okay? All right, any questions about this? All right, so we're going to use this definition and carry it forward, and we're going to use this idea in place of m. So let's take a few examples, and we're going to start with the growth function for the linear perceptron. Now, this is just the perceptron in 2 dimensions because you have to kind of illustrate it in the simple case before you can talk about it in the more complex case. And so here we have a data set of size 3, right? Now, of course, with a data set of size 3, we know any growth function for a hypothesis set is going to have its maximum at 2 to the 3 because n equals 3, which is just 8. 2 to the 3 is 8. So if we take our linear perceptron and we take our data set of size 3, we want to know, does that linear perceptron, can it produce all possible 8 labelings on a data set of size 3? Well, okay, well, we have this labeling. The perceptron is on one side of all the points. So that would be -1, and everything would be +1. Then you could do the converse where the perceptron is above all of those points. They would be -1, and nothing would be +1. Then you could have the perceptron cut one of them off. That would be -1, that'd be +1. And then you could have the flipped side, that would be +1, and that would be -1. So if you count all those ways of producing dichotomies, you have 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? And so, yes, absolutely. If you take the linear perceptron as a hypothesis set, it can produce all 2 to the 8 labelings. Does that make sense? Okay, so yes, it can fully describe all the labelings on a data set of size n equals 3. Now, let's take a look at this arrangement. Now, remember, when we talked about this idea of a growth function, we didn't set restriction on what the feature values are. In this particular case, the feature values were chosen so that all of these data points are collinear, right? They're on a straight line. Now, certainly, the linear perceptron cannot create this labeling. But remember, when we talk about growth function, we don't talk about a particular arrangement. We say, what is the arrangement such that you have a maximal number of dichotomies, right? So you can always rearrange the geometry in an advantageous fashion to try to maximize the number of dichotomies that your hypothesis set can generate. Does that make sense? Okay, so if we go from a data set of size 3 now to a data set of size 4, we see something happens. Well, if we look at the maximum, the upper bound, well, we have 2 to the 4, which is 16 different dichotomies, which is the maximum the growth function can be, or the number of dichotomies, if you have a data set of size 4. Now, if you do that same analysis with your linear perceptron, we'll notice something happens here, right? The perceptron can only generate 14 of these 16 dichotomies. You're going to have this one, there's 2 of them for here, where it's here and here, and then you have the individual, so that's 2, that's 4, 6, 8, 10, and then 12, 14, right? And when I say count 2 at a time, it's pluses on this side, minuses on that side, pluses on that side, minuses on that side. Does that make sense? And so the linear perceptron, once you get to a data set of size 4, it can no longer keep up, if you will, right? It can no longer generate 2 to the n dichotomies. It breaks. You broke the perceptron when you went from 3 data set of size 3 to a data set of size 4. Okay? Does that make sense? And so this idea of a breakpoint, right, is that point in the data set size when a hypothesis set can no longer generate all 2 to the n dichotomies for that data set. Does that make sense? Okay. So if one hypothesis set has a larger so-called breakpoint than another hypothesis set, that means that that hypothesis is more descriptive and therefore stronger or more powerful. Does that make sense? Okay. So let's take a look at some simple examples just to show you, now these are just made up examples, they're in the book, but to show you this idea about the relationship between the growth function and the complexity and the number of dichotomies that a more complex hypothesis set is able to generate. So in this example, we have what's called the positive rays. And the positive ray has a single parameter A, and that's what we'll call the anchor point. And so if you set A to a particular value, right, the ray extends out in infinity to the right as the number gets bigger. And everything to the right of the anchor point A is going to be labeled as a +1 label by the hypothesis. Everything to the left of the anchor point A is going to be labeled as a -1 a label by the hypothesis. So here we have a set of real values. And if you mathematically want to write it, it's just sine of x minus a. Functionally, you can actually implement something like this in MATLAB pretty easily. And if we look at the growth function, what we want to look at is the number of dichotomies that the hypothesis set consisting of the set of positive rays will generate. So if we think about this, how do we generate plus and minus dichotomies? Well, if you set the anchor point, the consideration is where are all the different places where you can set the anchor point? Because where you set the anchor point is going to produce a different +1, -1 labeling. So if we have n many data points here, right, we look at the gaps between each of these x values, our one-dimensional features. So we have 1, 2, 3, 4, up to and including n, right, +1 to the left, to the right of n. So that's n plus 1 different places where we can put the anchor point A, right? If there are n plus 1 places where we can put the anchor point for the positive ray, each anchor point setting results in a different labeling of +1, -1. So we have a growth function describing the number of dichotomies as being n plus 1, where n is the sample size. Does that make sense? Okay, so this is a very simple hypothesis set. And you'll notice here that, there's only one parameter really that we can modify, the anchor point A. All right, does that make sense? So let's take a look at something that's a little bit more complex. Let me time check. Let's look at the so-called positive intervals. Now, the positive intervals, it's another hypothesis set. It's more complex. It has two different anchor points. Let's call them the left one and the right one. You can call it A and B if you want to. It doesn't matter what you really call it. And the semantics of the positive intervals hypothesis set is such that you choose a left anchor point, you choose a right anchor point, and all of those in-sample points whose values fall between the left and the right anchor points, those are going to be labeled +1 by the hypothesis. And all of those in-sample points whose values are outside of the left and right anchor points, to the left and to the right, those are going to be labeled -1 by the positive ray. Does that make sense? Okay. So if we think about this, now we want to count the number of dichotomies that this positive interval can generate. So what defines a positive interval? The placement of these two anchor points, the left anchor point and the right anchor point, because wherever you place them, between them is going to output a positive, +1 label. Outside of them is going to output a -1 label. So therefore, we can count the number of dichotomies by counting the number of placements of the left and right hand anchor points for our positive interval. So if we think about it, okay, well, if we have a data set of size n, x1 up through and including xn, we look at all of the gaps between our in-sample points in one dimension. So we have 1, 2, 3, 4, n, and then that last part, another one. So we have n plus 1 possible gaps. Now, to count these placements, we have two choices. We place the left anchor point and we place the right anchor point. So that means out of this n plus 1 many data points, or gaps, or intervals, if you will, we're going to choose two of them. And that's one, we're going to replace the left anchor point, and the other, we're going to place the right anchor point. Does that make sense? Okay, so we have n plus 1 choose 2. That corresponds to the number of placements of those two anchor points left and right among the n plus 1 many gaps that we have to choose from. But we're not done with that, right? We also have to account for the case where you place the left and right anchor point in the same space, in the same gap. So if you place the left and right anchor point both in this gap, so left goes here, right goes in the same gap, all of a sudden, nothing is labeled +1, the blue, and everything is labeled -1. And that's the same regardless of where you place them. So we'll count that as one type of placement. We have everything is red and nothing is blue. Everything's -1 and nothing is +1. Does that make sense? So if we count all the possible dichotomies that you can generate with a positive interval, we have n plus 1 choose 2 +1. We do the algebra, right? So if we're going to do the algebra, you get, let me get my marker. Forgot to grab my marker beforehand. So n plus 1 choose 2 plus 1. That's n plus 1 factorial over n plus 1 minus 2. That's n minus 1 factorial over 2 factorial plus 1. Well, n plus 1 factorial, let me just erase that. That's n times, n plus 1 times n minus 1 factorial. N minus 1 factorial cross out. So you have 1/2 n times n plus 1. And then that plus 1 stays out there. So that's 1/2 n squared plus 1/2 n plus 1. And that's our result. Okay? And so if we look at this, the positive intervals, it's more complex. It has two parameters, right? And because it has two parameters, it's more expressive than the positive rays. And if we look at its growth function, you'll notice our growth function for the positive intervals, it's quadratic, right? Whereas the growth function for the positive ray, it's linear. A quadratic is more um, complex than a linear function, right? And therefore, because the positive intervals is more expressive, it's a stronger hypothesis set. It can produce more dichotomies than the positive ray. Does that make sense? Okay, so we have the positive interval. Let's continue on and do something even more complex. Let's talk about the set of convex sets. Now, a convex set is just a linear combination, and we'll take this convex set. Recall that when we talk about growth functions, we don't make any assumption about the geometry among the data points. And so what this construction does, it says the hypothesis set is a set of convex sets in the plane. And how we're going to construct this with a regular construction is as follows. So we start, with a circle, and we put all of our n many data points around the circle. It doesn't matter where on the circle they are, and it doesn't matter what the labelings are. You could have it alternating plus, minus, plus, minus, plus, minus. You could say plus, 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 minus, 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 or any possible arrangement of labels to your in-sample points. The only requirement is that they have to be on the circle, right? Some could be close, some could be far. It doesn't matter what the labelings are or what that positioning is, but they must be along a circle, okay? Now, you take these points along the circle, and then you identify all the points that have a +1 label, and you draw a line segment connecting each one of the +1 labels going around the circle to one another. So in this assignment, we have a plus, we draw a line to this plus, a chord here, and a chord here, a line cutting across, connecting all the plus labeled points together with one another. So then what you do is you draw the convex hull, or calculate the convex hull that you create when you draw all the chords connecting all of the plus labeled points. And then any data value or data point value or features corresponding to points that are inside of this convex hull, this hypothesis is going to output a +1 label, and anything outside of this convex hull is going to output a minus label. Does that make sense? Okay, so if you look at this, it's a lot more complex. And if we think about all the possible dichotomies that this can produce, well, we set no restriction on the way you label it. So we have available all 2 to the n possible labelings of the data points. You agree? All possible 2 to the n labelings we have, the data points we can draw around a circle. The only requirement was that they're around a circle. It doesn't matter what the geometry is. You just have to choose a geometry where you can maximize the number of dichotomies that your hypothesis set produces. So in that particular case, we have 2 to the n, all 2 to the n possible labelings. So this particular hypothesis set is perfect in terms of its ability, fully expressive. It can express any possible labeling of +1, -1 of our n many in-sample points, and therefore can produce all 2 to the n dichotomies. Does that make sense? And so if we look at the convex set, that hypothesis, it's a lot more complex and it's a lot more expressive. It's perfectly expressive, if you think about it, relative to the positive interval, which is more expressive, but less than the convex sets, which also positive ray was the least expressive. And if we look at it, the growth function for positive ray, it's linear. The growth function for positive interval is quadratic. And the growth function for convex set is exponential in the sample size. Okay? All right. Any questions about this? So this idea of growth function, as we said before, when we're motivating the idea of making it a lot more tractable, it effectively collapses down what it means to be a hypothesis. When we count hypotheses to look at the complexity of the hypothesis set, we're only counting things that are different in terms of the labeling of the in-sample points. Okay? All right. So let's take a look at this idea of a breakpoint. We talked about growth functions, and these growth functions, they're nice, but they're formulas, and these formulas are useful. But it'd be nice to have a single number that we can use to draw comparisons between, say, the convex sets or the real interval versus the positive ray, the positive interval versus the positive ray. So to recap, we had the positive rays, the growth function, was n plus 1. It was linear in the size of the set of in-sample points. We had the positive intervals. It was quadratic in the sample size, in sample points. And then convex sets, it was exponential, and it satisfies the upper bound in terms of fully expressiveness of the ground truth labelings. Okay, so we're going to introduce this idea of feasibility. Now, if we use our growth function as a replacement for m, where m before was the size of the hypothesis set, essentially what we're doing is we're replacing this m from the union bound with the growth function. And from the looks of the rest of the union-bound version of Herting's inequality, corresponding to the multiple hypothesis case, where you have your learning algorithm searching through the space of hypotheses for the final best hypothesis, if we look at this exponential, we make an observation. As long as this growth function is polynomial in its form, then if you get enough samples, you can always guarantee that this negative decaying exponential is going to eat away at the complexity introduced by the hypothesis set, its expressiveness, and make this right-hand side of the inequality very, very small. And that was a desirable quantity because what that means is that if this right-hand side of the inequality is as small as we can get it, that means E in diverging from E out is going to be a rare occurrence. And that's exactly what we want, is that most of the time, we want the out-of-sample performance to track well or follow the in-sample performance, because all you can control are your learning algorithm and your hypothesis set. So this idea of the growth function is a nice approximation to this worst case, kind of tightens up the bound a lot, because you don't really need to consider every single hypothesis. You only need to consider hypotheses that are different in their labeling of the in-sample points, how they dichotomize. Does that make sense? And so now we ask the question, is learning feasible, right? Can you get good out-of-sample performance? And we learned last time that you can get good out-of-sample performance if you can reasonably guarantee that in-sample error, which you have control over, right? Because you can choose the error function, you can choose the hypothesis set, you can choose the learning algorithm. If you can guarantee or be reasonably confident that in-sample error is going to out-of-sample error is going to be very close to in-sample error, then that means you're going to generalize well, right? You're going to perform well out-of-sample. And one way of doing that is by ensuring that the complexity of your hypothesis set is polynomial. Because if it is polynomial, by choosing your data set size, your in-sample points, to be large enough, you'll always make sure that divergence is a very rare occurrence. Does that make sense? Okay, any questions about this? Okay, so this idea about the growth function, we're going to use as our proxy for complexity of the hypothesis set. And in doing so, you're going to make this much more feasible, through a tighter bound. And so there's a term called the breakpoint. And what the breakpoint is you'll recall when we had the linear perceptron in the plane, when we went from a data set size of 3 data points to 4 data points, the perceptron could no longer keep up. It could no longer generate 2 to the n of the possible dichotomies. And we use the terminology, it broke, right? And so we're going to introduce a term called the breakpoint. And the breakpoint represents that data set size where the growth function can no longer keep up with this 2 to the n upper bound. Does that make sense? And so we're also going to introduce another terminology called shatter. To shatter means to produce all possible dichotomies for a data set of size k, right? And so you can imagine all your data points. Imagine if it were on a piece of glass, right, in 2 dimensions, and I just draw data points on it. And let's say, I could take a hammer and I hit that piece of glass, and it's a weird hammer in that regardless of how I break this glass, I will always break it into 2 pieces, right? And so I can break it into 2 pieces a lot of different ways. How many ways? In 2 to the n, many different ways. And so a hypothesis set, so-called, shatters a data set if it can break that data set into 2 groups, the +1 labels and the -1 labels, in all 2 to the n possible ways. And so the breakpoint is that data set size when your hypothesis set can no longer shatter the data set, right? And so when we went from a data set of size 3 to size 4, that's when the linear perceptron could no longer shatter, right? And therefore, we call 4 is the so-called breakpoint for the linear perceptron. Does that make sense? Any questions about this? And so now, this idea of a breakpoint gives us a single number that we can use to compare the descriptive power of two different types of hypotheses, right? Okay, so for 2D perceptron, K was 4, the breakpoint. It was that data set size at which it could no longer shatter our data set, okay, or produce all possible 2 to the n dichotomies or labelings. Okay, so let's go back and look at the growth function and consider what happens with this new way of thinking about descriptive complexity or the power, if you will, of a hypothesis set. We're going to look at the breakpoint and compare that to our growth function from before. So for the positive ray, it has a breakpoint of 2. So that means once your data set is of size 2, the positive ray can no longer produce all possible labelings, right? So, all right, well, if the breakpoint is k equals 2, what happens at k equals 1? Well, if you have one data point, what is your alternative? You can either color it blue, +1, or you can color it red. Well, with a positive ray, you said you choose an anchor point. If that anchor point is to the left of that point, well, it's blue. If it's to the right of that point, well, it's red, right? And so you can produce all 2 to the k equals 1, 2 to the 1 is 2. You can produce all 2 to the n dichotomies for a data set of size 1 for the positive ray. But when you go to a data set of size 2, well, 2 to the n, 2 to the 2 is 4, it cannot produce all 4 dichotomies. Let's think about that. If you have 2 data points, well, the positive ray can anchor to the left of both, calling them all blue. It can do it to the right of both, calling it all red, or it can do in between, calling one red and one blue, but not vice versa, right? And so it can only produce 3 of them, so it breaks. It can't shatter all possible dichotomies. Question? So the positive ray, let's think back to the semantics of the positive ray. And the question is, why can't it produce all 4? So you have your data points. And let's say this is my first data point, x1, second data point, x2. And the positive ray, let me just do it that way. The positive ray has an anchor point we called A, right? And so if you put your positive ray A here, the positive ray, it extends out to infinity to the right, and everything to the right of the anchor point, it calls positive. So if the anchor point is here, it'll say plus, plus, and everything on this side is minus, right? If the anchor point is here, the positive ray will say this is minus, minus, and everything here is plus. If the positive ray has its anchor point between x1 and x2, it'll call x2 positive, x1 negative. But it can't call x1 positive and x2 negative. It's not able to generate that dichotomy. Okay? So when we go to from a data set of size 1 to size 2 for the positive ray, right, it breaks when the data set goes to 2, and therefore its breakpoint is 2. Does that make sense? Okay. So for the positive intervals, its breakpoint is 3. If we look at what happens for a data set of size 1, one data set, it's either +1 or -1. Well, the positive interval, remember the semantics of the positive interval, it had 2 anchor points, right? It had the left anchor point, and it had the right anchor point. Everything between the left and right anchor point, it called it a plus. Everything outside, it called it a minus to the left and right of the anchor point. So if we think of a data set of size 1, well, it can either have both anchor points to the left, right, or the anchor points straddling that one data point. If we have a data set of size 2, well, you can produce all 4 possible dichotomies. You can produce all of these red, all of these minus, all of these plus. You can say 1 is plus and 1 is minus, or have the 2 anchor points between in the gap, and they're both minus, right? But when you go to a data set of size 3, well, it can't produce all 8 dichotomies because the way this positive interval is, it calls everything in the middle plus. So there's no placement for the left and right anchor that you can make to make the center point at k equals 3 to make that red. It's not possible to do that with the positive interval. Does that make sense? Okay. And I would recommend you try it yourself on paper. That's why these are deliberately simple, so you can actually try it yourself. Okay. So with a breakpoint of 3, well, what happens? If we look at the expression for the growth function, right? Remember, the growth function describes the maximum number of dichotomies. If you plug in k equals 1 into the growth function for positive intervals, well, that's 1 squared, so that's 1/2 plus 1/2, that's 1 plus 1 is 2, right? All 2 dichotomies. If you plug in k equals 2 into the growth function for positive interval for a data set of size 2, well, that's 1/2 of 4, that's 2. 2 plus 1/2 of 2 is 1. So 2, that's 3, plus 1 is 4. It can produce all 4 dichotomies using the growth function. Now when you plug in k equals 3, well, when k equals 3, the number of dichotomies, the upper bound is 2 to the 3, which is 8. If we plug in 3 into the growth function, the maximum number of dichotomies produced by positive intervals hypothesis set. So that's 3, that's 9, that's 4.5, plus 1.5, 5.5, 6, plus 1 is 7. It can only produce 7, right? It can't produce all 8. So therefore, it breaks at k equals 3. So the breakpoint of positive intervals is 3. Okay? And then lastly, for the convex sets, we have the growth function is 2 to the n. It doesn't matter. It doesn't have a breakpoint, and it's called an infinite breakpoint because it can produce at all data set sizes all possible 2 to the n dichotomies. And if we look at them, that verifies our idea, right? We were talking about the growth function being linear versus quadratic versus exponential. And now we have a single number, the breakpoint, where we can now rank the complexity of these different hypothesis sets. Does that make sense? Okay, any questions about this? No? No questions? All right. So if there's no breakpoint, or if there's a so-called infinite breakpoint, it means the growth function is exponential, 2 to the n. If there is any breakpoint, that means the growth function is polynomial in the input sample size. And if we go back, well, you could say the positive raise is linear, and that's simple subpolynomial, if you want to call it that. Positive interval is polynomial. Quadratic is a type of polynomial. And we see the convex sets, that's exponential. And so in order to have a breakpoint, that means that your growth function is polynomial in the number of data points you have, your in-sample set size, the size of your in-sample points, the size of the set of your in-sample points. And so now, if we ask the question, is learning feasible, we can now turn that to a test to see, does a breakpoint exist? And does a breakpoint exist means your growth function is polynomial. So now all we need is a test to see if the growth function is polynomial, and that is equivalent to saying, does a breakpoint exist? And if a breakpoint exists, that means learning is feasible. Okay? All right, any questions about this? Okay, so that's it for the module for today, and we'll pick back up with this and further this discussion. It's 5:34, we'll end early. I will see you on Thursday, and please look out for the Slack